Within this section, we introduced VLAN principles as a means of logical isolation at the data link layer. So a virtual local area network, or VLAN, represents a form of administrative network that defines a logical grouping of hosts or end system devices that are not limited to a physical location and may be defined based on a wide range of parameters that allow for a greater flexibility in the way that logical groups are defined. The application of VLAN technology has expanded to support many aspects of enterprise networking as a means of logical data flow management and isolation. So upon completion of this section, it is generally expected that trainees will be able to explain the application of VLAN tagging, describe the different port link types and characteristics, as well as successfully establish port-based VLANs. The growth of an enterprise network represents a general increase in the number of end stations that are connected to the access network, which in turn involves an increase in user traffic. As demonstrated in this example, the local area network can be understood as one big broadcast, in which link layer broadcast traffic generated by an end station is summarily propagated throughout the local network, regardless of which IP network hosts belong to. With the increase of end stations, this in turn increases the number of broadcasts generated and causes the local network to get very noisy, which can lead to network performance issues. The obvious solution is to control the size of the local networks and limit the scope of layer 2 broadcasts. While this is possible through implementation of routers, which act as gateways between local networks, routers unfortunately do not provide the same level of efficient forwarding as found with switches. Resolving the issue of traffic management at the link layer has eventually led to the creation of virtual local area networks. So rather than rely on layer 3 technology to define the boundaries of the broadcast domain, VLAN technology is used to logically isolate traffic at the data link layer. This means that switches can be configured to associate links based on VLAN groups. Traffic from end stations associated with a group would only be able to forward link layer traffic and link layer broadcasts over switch interfaces that are considered part of the same group. From this example, we can see how broadcast traffic is generated by a host that is part of a group, and that transmissions from a host within that group can only be received by end stations that are considered part of the same group, meaning that layer 2 traffic is logically isolated as a result of VLAN-generated broadcast domains. One of the other important factors of VLAN technology is in its ability to associate end stations with a certain VLAN group, regardless of the end station's physical location within the network. This allows a greater level of flexibility when it comes to traffic isolation at the data link layer. The creation of such groups of VLANs is achieved through the insertion of a set of instructions within the frame header. In the case of a tagged frame, we see a tag inserted between the source MAC address and type field of the Ethernet 2 frame. The frame tag includes a tag protocol ID that defines the tag format. However, since there is only currently one format, this does not change. Some traffic is prioritized over other traffic, such as in the case of voice and video data carried over the IP network. If such traffic is to be given preferential treatment, the frame may be set with a priority level. The priority code point, or PCP, is used to represent this priority level for the frame. It is used together with a drop eligibility indicator, or DEI, that determines whether the frame should be dropped if congestion occurs in the network. More relevant at this point in time, however, is the VLAN ID that represents which group, or VLAN, the frame belongs to. This is a 12-bit field that allows potentially up to 4,096 VLAN IDs to exist. However, protocol standards define some of the VLAN IDs in this range to be reserved. There are two link types that are found within VLAN technology. These are the access link type and trunk link type. The access link type refers to the link that exists between a switch and an end station, while the trunk link represents the links that exist between switches. Each port interface on the switch must be associated with a VLAN. This applies to interfaces for both access and trunk links. A port VLAN ID, or PVID, is the number that is used to associate each port interface on the switch with a VLAN. If this is not manually configured, the PVID of 1 will be used by default. The PVID will determine the behavior that is applied to frames as they are transmitted and received on a port interface. We can use the example shown to explain the application. You can see for the access links, the PVID has been changed to be associated with either VLAN 2 or VLAN 3. This means that the frames from hosts associated with such access links will be considered part of the VLAN to which they are connected and be tagged as such. In the case of the trunk link, this has been maintained with a PVID of 1. A switch supporting VLAN technology may apply one of three port types to each port interface. The port types are used to specify the tagging behavior that is applied to the frame on the switch interface each time a frame is received or is to be transmitted. We start off here by looking at the access port type that is used on ports associated with access links. We can see from the example that each port interface is associated with a PVID that represents the VLAN with which each port is associated by default. The links associated with host A and host C are both associated with the PVID of 10. In terms of behavior, any untagged frame that is received on an access port interface will be tagged with a VLAN tag associated with the PVID for that interface. In this case, the transmission of a frame to the switch by host A will be received by the switch that will associate the frame with VLAN 10. It will determine the forwarding behavior to be applied based on whether the frame is considered part of the same VLAN. If, like the port interface associated with host C, in which this same PVID is used, the frame tag will be removed and the frame forwarded. If the port interface, however, contains a different PVID, such as the PVID of 2 that is associated with the port interface on which host B is connected, the frame will be restricted from being forwarded via the port. Interfaces associated with trunk links may be associated with the trunk port type. Once again, a PVID is associated with each of the port interfaces on the trunk link, and the trunk port type determines the associated trunk port behavior. We demonstrate here the condition in which two separate VLANs exist on a switch in the form of VLAN 10 and VLAN 20. These have been configured as the PVID for ports associated with host A and host B. The trunk port on the switch that relates to the trunk link between switch A and switch B is set here as part of VLAN 10. Frames received on access ports may either be tagged as part of VLAN 10 or VLAN 20. Where frames are tagged as part of VLAN 10, the trunk port, prior to transmission, will remove the tag and transmit the frame over the trunk link. This occurs because the frame received from host A is considered associated with the default VLAN of the trunk port. For frames tagged with VLAN 20, however, the tag frame is seen as part of another VLAN, and therefore will be transmitted as a tag frame over the trunk link. The hybrid port type is the final port type that may be used within VRP and represents the default port type used. This port type is capable of being used on both access and trunk link types, however provides somewhat more flexibility in the way in which the behavior is applied in the VLAN tagging process. We associate each of the interfaces with the same PVID as has been used in the previous port type examples. However, in this instance, all interfaces are considered hybrid. The distinction is made based on whether the hybrid port is considered tagged or untagged. For simple definition, we can assume that access port types are untagged, whilst the trunk link types are generally considered tagged. The untagged hybrid port types, like access ports, will add tags to receive frames and remove tags from frames being forwarded to end stations that are not aware of VLANs. Tagged hybrid ports, on the other hand, operate in a manner similar to that of the trunk port. However, in this case, we find that all frames are tagged regardless of the VLAN that the frame belongs to. If we take a look at the PVID for trunk port interfaces on the trunk link between switch A and switch B, the PVID remains as 10. However, unlike the trunk port, the frame remains tagged. The same applies to frames tagged as part of VLAN 20. One of the key capabilities of the hybrid port, however, is its ability to selectively define on untagged ports which VLAN should be allowed to be forwarded over the port. In the case of host D, we will notice that the frames originally associated with VLAN 10 and VLAN 20 are both able to be received as a result of privileges being assigned to this port. Frames received from host D, however, will be tagged as part of VLAN 20 based on the PVID of the receiving port. The way in which end stations are associated with a VLAN is achieved through one of 5 methods. The port-based assignment method that we have just introduced along with the port types is the most common method of VLAN assignment, which determines the VLAN associated with VLAN frames as a result of the PVID association with each port. It is possible, however, to also determine the VLAN to which received frames should be allocated based on other parameters, such as the MAC address of end stations. The received frame in such cases will assess the source MAC address to determine the VLAN to which the frame should be assigned to. The same principles can also be applied to the IP address that can perform VLAN assignment based on the network to which a host belongs. Protocol-based assignment is applied where multi-protocol environments exist, such as in the case of TCP/IP and the novel network protocol suite that employs the IPX protocol. The final method is a policy-based method in which a combination of IP subnet, port, and MAC address can be used to provide a match rule that will determine the VLAN to which an end station with matching parameters will be allocated. Taking these VLAN principles into account, we can begin to look at how VLAN technology is applied to the Ethernet network. We begin generally by creating the VLAN on the switch. Ports cannot be associated with a VLAN until the VLAN is created. So we show here two methods for creation of the VLAN. Here we use the command VLAN 10 to create a single VLAN called VLAN 10 within the switch. Alternatively, if we wish to create multiple VLANs, we are able to apply the VLAN batch command. In this example, the batch command is used to create a range of VLANs from VLAN 2 to VLAN 3. If required, however, it is also possible to use the batch to create discontiguous VLANs, using the same VLAN batch command followed by each VLAN to be created, separated by a space. Once the required VLAN has been created, the creation of the VLAN can be verified through the display VLAN command as we see here. We should notice that as a result of the configuration, there are now 4 VLANs present within the switch, those being the 3 VLANs created and the default VLAN, VLAN 1, with which ports are associated by default and show us either in an up state or a down state. In this example, however, we have simplified the list to show only the first port. The created VLANs 2, 3, and 10 are also shown to exist, however they are currently not associated with any port interfaces. The setting of the port link type refers to the assigning of the port type for the interface. This by default in VRP is set as hybrid, and therefore it may generally be considered necessary to change the port type where either a trunk or access port type is to be used. This configuration is achieved under the port interface view for the port interface that is to be set. We consider that the link between switch A and switch B shall be a trunk link, and therefore we set the port link type to trunk for the associated Gigabit Ethernet 0/0/1 port. In the case of port interfaces associated with end stations, we shall set these to operate as access ports. Interfaces can be assigned to VLANs once the VLAN has been created. There are in fact a couple of ways in which this can be performed, and in this example we can see the two methods of configuration that can be used. The first involves initially creating the VLAN, and under the VLAN view, specifying directly the port interfaces that should be associated with the VLAN. As such, we are able in the first instance to assign port interface Gigabit Ethernet 0/0/7 as part of VLAN 2. The alternative method is achieved under the interface view, via which we first define the port link type that should be used initially, and using the command port default VLAN followed by the VLAN number with which the port is to be associated, we are able to achieve the same result. In both instances, the PVID of the port interface is set. Once the VLAN has been created and the port interfaces have been associated with a VLAN, we need to determine whether the configuration has been performed correctly and taken effect. We can again use the display VLAN command to verify this, in which case we should find that the configured port interfaces are now associated with the VLANs to which they have been assigned. Currently, we have seen how the port interfaces Gigabit Ethernet 0/0/7 and Gigabit Ethernet 0/0/5 have been assigned to VLANs 2 and 3 respectively. The configuration of the trunk link follows the same configuration principles as were used to configure the access port interfaces. Since we have already created the VLAN to be used, it is now only necessary that we assign the trunk port interface to that VLAN. In this case, we have assumed VLAN 10 to be the VLAN for the trunk link, and therefore need to set the PVID to 10 for port interface Gigabit Ethernet 0/0/1. For traffic to be carried over the trunk link, however, a rule needs to be set that states whether the tag frame received by the trunk port are permitted to be forwarded or not. In this instance, we have configured this rule to allow frames tagged as part of VLAN 2 or VLAN 3 to pass over the trunk link. Frames tagged with any other VLAN tag will be restricted. This rule also stands for VLAN 10, even though it is the default VLAN for the trunk link. If we again return to the display VLAN command output, we are able to see the effects of the VLAN configuration for the trunk link. In this instance, we are able to see that interface Gigabit Ethernet 0/0/1 has now been associated with both VLAN 2 and VLAN 3. We are able to distinguish the access ports from trunk ports based on whether the port interface is considered untagged by the UT or tagged by the TG variable displayed before the interface. This means that traffic from VLAN 2 and VLAN 3 is permitted to be carried as tag frames over the tag trunk interface of Gigabit Ethernet 0/0/1. Until now, we have implemented VLANs based on access and trunk port link types. Unfortunately, however, for access ports that are associated with a VLAN, they are only capable of receiving frames associated with the configured PVID. This can be considered something of a restriction that results in an inability to receive VLAN traffic across VLAN boundaries. With hybrid ports, however, we are able to apply a greater level of control of what frames can be received by an end station, regardless of the VLAN with which a frame is associated. Initially, however, it is important we understand the configuration involved with setting up hybrid VLANs. Again, it is necessary to ensure that the VLANs have been created, and where they exist, the port link type of the port interface is set to hybrid. The hybrid port link type is set as the default port link type in VRP, however, and so may not be required to be configured. For relevant interfaces, however, we should set the port hybrid PVID VLAN command to specify the VLAN with which a port interface should be associated. Interfaces should be configured as either tagged or untagged, which effectively sets the behavior of the port interface. A tagged interface operates similarly to a trunk port, whilst an untagged hybrid port operates like an access port. However, in both cases, the behavior is not identical. Interfaces associated with end stations should be set as untagged, while the trunk port should be configured as a tagged port. Here we can see the untagged configuration of the access links for interfaces Gigabit Ethernet 0/0/5 and 0/0/7. For the trunk link, we apply the tag parameter to the command and specify the VLANs that are to be carried over the trunk link. In this case, we are again allowing VLANs 2 and 3. When we use the display VLAN command, we will see pretty much the same information as was found when using the access and trunk port types. Frames received on interface Gigabit Ethernet 0/0/7 will again be assigned as part of VLAN 2, and frames from interface Gigabit Ethernet 0/0/5 as part of VLAN 3, and in both cases are considered untagged ports. The port interface Gigabit Ethernet 0/0/1 is considered a tagged port interface for VLANs 2 and 3. From the previous examples, we should have a good sense of how the hybrid interface is configured to allow interfaces to associate with a PVID, and how to allow frames to be carried over the trunk link. The example shown here, however, takes this a step further and demonstrates one of the primary features of the hybrid port. In this case, we refer to switch B, and in particular interface Gigabit Ethernet 0/0/4 that is associated with host D. In this instance, the port link type is again hybrid, and the PVID for the interface is VLAN 3. We find, however, that the hybrid untagged VLAN command is associated with both VLAN 2 and VLAN 3. So what does this mean exactly? Well, it means that frames, more commonly broadcast frames originating from VLAN 2 and VLAN 3, will have the tag removed from the frame header, allowing the frames from both VLANs to be received by host D. Frames transmitted by host D, however, will be associated with VLAN 3, based on the port PVID. This allows flexibility of frame transmission that is not possible with the access link type. If we take a look at the results of this once again through the display VLAN command, we will find that the port interface Gigabit Ethernet 0/0/4 is clearly untagged and associated with both VLANs 2 and 3. This basically means that frames containing either VLAN 2 or VLAN 3 tags will be untagged and forwarded over this interface. IP convergence is a large part of today's enterprise networks, and so we find the enterprise network now not only needs to support the communication of IP data, but also incorporate a number of other technologies that are not native to the IP network. In particular, we can consider the transport of voice through the IP network. Originally, the transmission of voice was performed over a separate telephone network, which generated a single dedicated physical circuit between the caller and receiver. Such networks are known as circuit switch networks, while the IP network is considered packet switch. The packet switch network, in contrast, involves call transmission transmitted in data blocks that may not take the same route through the network, resulting in packets being received out of order. Additionally, the packet switch network works on the basis of contention, which is not ideal for traffic that is sensitive to delay. It is therefore necessary to allow some level of privilege to be given to such voice traffic in IP networks to allow it to be transmitted as smoothly and with as little delay as possible. This requires that voice traffic be distinguished from other IP data so that it can be classified and treated with priority. The isolation of voice traffic is supported through the creation of voice VLANs that allow packets containing voice data to be isolated and prioritized as a means of ensuring as little delay as possible. The establishment of a voice VLAN requires initially that a VLAN be created through the VLAN command, and then set to operate as a voice VLAN. We demonstrate here how this is achieved from the perspective of switch B. Enablement of the voice VLAN is performed on the interface, which in this case is interface gigabit Ethernet 0/0/1. Voice VLANs are able to support different working modes that allow ports to be added to the voice VLAN. A port may also receive more than just voice traffic, and so to distinguish between the different forms of data, the MAC address of voice-enabled devices, such as an IP phone, is used, and associated with the voice VLAN. We can use the command display voice VLAN status to verify the configuration parameters have taken effect. Since a VLAN is adapted to become a voice VLAN, we must verify that the state of a created VLAN is now considered a voice VLAN. Here we can see that voice VLAN 2 has in fact been created and is considered enabled. The voice VLAN can be considered to be associated with port interface gigabit Ethernet 0/0/1 and is operating in an automatic add mode, meaning voice devices connected to the port will automatically be associated with the voice VLAN. Some other features include the security mode that checks the MAC of the received frames to make sure that they match the OUI defined in the previous configuration steps. If the interface is to support communication to other vendors, the legacy option will be made active. In summary then, for this section, we just have a couple of questions here. The first asks, if a trunk link has a PVID of 5 and the command port trunk allow pass VLAN 2 and 3 is used, which VLAN traffic will be carried over the trunk? Well, only VLANs that are permitted to transmit over the trunk link are able to transmit. Even though VLAN 5 is the default VLAN for the trunk, only VLAN 2 and VLAN 3 frames will be forwarded. What action will be taken by an access port with a PVID of 2 when receiving an untagged frame? Well, the received untagged frame will be associated with the VLAN referenced by the PVID of the access port, which in this case is VLAN 2. This means that a tag with a VLAN ID of 2 will be inserted into the frame before the frame is processed further by the switch.